Hello everyone, my name is Ahmed El Amine Djebri. I'm a PhD student at Université Côte d'Azur and a member of WIMIC's research team at INRIA Sofia Antipolis Research Center. In this video, I'll be presenting our work about task-oriented uncertainty evaluation for linked data based on graph interlinks. This work is co-authored and supervised by Andrea Tettamanzi and Fabien Gandon. And this work is introduced within a context where web-based applications are emerged everywhere, a context where linked Open Data Cloud counted more than 1,200 linked datasets, but also a context where data sources don't often present what is wrong with their data, simply because they trust it blindly or they have no means to evaluate that. And for users, not trusting the web is understandable. Users are more and more into looking somewhere else to confirm information they get from one data source, especially if it's new to them. The same trust issue extends to the semantic web. And I always like to illustrate that trust issue with a simple query linking the French and the English chapters of DBpedia, where more than 10% of the football players we checked have a different height values between the two chapters. Now, to avoid check-in and confirmation being done by the users, and for each and every one of them, sources should provide more information about how much they trust data they are providing, whether it's their data or links they provide for external ones. This was the spirit of the work surveyed by Paul Heim, where he classified error detection in knowledge graphs and classified the approaches into internal ones using their own data to detect anomalies and external ones, either by crowdsourcing or comparing the data to other references. Now let's focus on the latter. We think the same thing should be done by a source when asked about a certain subject, for it to check with other references whether it's reliable before serving the user. And assessing its expertise or the uncertainty of its data requires it to have a certain link with external resources. It's kind of the analogy of the student in the exam who wants to assess his own level and to check how much he does know and how much he is reliable on a certain subject. So this brings us to the need to evaluate uncertainty in a source according to a user preference or a certain task and compared to other external resources. And what we propose here, what we are presenting, is an external approach to evaluate uncertainty based on graph interlinks. Those are presented in a simple form of URI reuse as all same as links and or custom linking predicates. And each of the existing similarity links between the sources of information can be seen or backed by a set of evidence links. Instead of linking sources, evidence links connect statements, and they stand witness for the similarity. So the analogy here is as if the link between two sources is maintained by one cable in which there is a set of existing similarity links, the yellow cables. Moreover, each one of the similarity links is backed up or is backed by a set of evidence links. So the user implication or the task customization appears in the selection of a set of focus resources around which we're going to be building focus graphs to reflect the ideas linked to the questions that we want to ask to the source of data. And later on, the user also chooses a certain quality of evidence links that he wants to accept from the source of data. And this, like the analogy, is like how to grade answers for students. For Whitney Houston, for example, questions might be about songs, asking for all details about each and every one, and one can choose to trust even lower quality evidence links. In our approach, we use concise bounded descriptions defined by Strickler to define focused corpuses of knowledge around focused resources. This RDF graph is assumed to be representative of the resource regarding the current use case. So to proceed, we need a reference source alongside with our target source. We also need a set of similarity links, linking focused resources from each source to the other, and we call it a contextual link set. First of all, we evaluate the transitive closure on both datasets and apply the definition of focus graphs to cluster data, accordingly to the focused resources provided in the contextual link set. We consider it as a preliminary step before evaluating object similarity. Now, for each pair of linked focus graphs, we evaluate the object similarity of between objects of each combination of statements. This score is considered as a preliminary quality of potential evidence link. The latter is confirmed as one if the quality surpasses the threshold. As output, we get for each pair of focus graphs a set of evidence links, for which we evaluate the predicate similarity. We try to find out the relationship between the predicate pairs, focus graph-wise, and see if that generalizes to all pairs of focus graphs. So we see whether the link is worth generalizing or not. To do so, we propose a set of indicators that help us see the relationship between the different evidence links, and we apply them both locally between pairs of linked focus graphs or globally to see the general effect. Indicators such as the participation of evidence links in the overall links or the average quality of all evidence links are ratioed, averaged, and weighted in a dot product to calculate the semantic similarity of two statements. Now, finally, in order to evaluate the contextual uncertainty or the uncertainty of target focus graphs, we combine both object and predicate similarity of all discovered elected outgoing evidence links from this focus graph. So in the end, as an output, we found ourselves with annotated statements with object similarity, with annotated focus graphs with contextual uncertainty values, and annotated predicate pairs with uncertainty values, and that can be used for future updates when new information is introduced. Combining all of these values can be done using the meta mapping modes that we mentioned in previous works. So in order to try and test our approach, we developed a tool we called Archer. It's an open source tool for uncertainty evaluation. It enables you to visualize, evaluate, and annotate data with uncertainty values. So we tested it on 714 pairs of focus graphs representing music artists from DBpedia and MusicBrainz. So the tool allows you to visualize the number of evidence links per similarity link and the numbers of admitted predicate pairs after threshold limitations. All of this result is pre-computed in one pass and visualized offline. It can also gives you an idea about the importance of the matching functions and help you decide what threshold to be used in order to get high quality links. So we still have a bunch of challenges, like what reference to select for a specific task, or what is the best focus graph to represent a certain resource. This opens a lot of perspectives in front of us. First of all, as a continuity of this work, we want to implement custom object similarity evaluation methods that vary in function of the type of the treated data. We intend also to represent the whole approach from a different perspective and try other evaluation metrics linked to other uncertainty theories. One of the most important things is to check the scalability of our approach and treat multiple references at once. So as you followed, I presented to you an uncertainty evaluation approach for data sources, which is based on graph interlinks and takes the user's perspective into consideration. We also offered the tool in beta called Archer for visualizing, evaluating uncertainty as presented and annotating data with uncertainty values. We are working to scale up to introduce more reference sources and more theories to our approach and to our tool. In the end, I would like to thank again the co-authors for their work, the organizers of EKAW for this opportunity. Thank you everyone. My name is Ahmed El Amine Djebri, and see you in the Q&As.